Hello. Over the next few minutes, we are going to discuss a technique or method called substitution to find solutions or compute solutions of ordinary differential equations. And this is substitution in the context of a particular family of equations named after the family of mathematicians Bernoulli. Okay. So these equations called Bernoulli are going to satisfy a particular form that we summarize here. The derivative of y, we assume y is a function of x, the derivative of y plus a term that involves the function y and has a factor or coefficient here called p of x. And then on the right side of the equal sign for this ODE, ordinary differential equation, we have the other coefficient or factor q of x, and then y raised to a power n. Now, we know that if that n is equal to 0, then this equation would be considered linear in both the function y and its first derivative. But in general, n is a number that in general can be assumed to be a real number. In some cases, like the example, the exercise we discussed in more detail here, n is actually an integer. So what we'd like to do is basically 3 steps. First, we're going to define a new variable, v, defined as a power of the function y, and this power is 1 minus n. Then we will compute the derivative and rewrite the equation, the derivative of a new variable, and rewrite this ODE as a linear equation of both v and v prime, its first derivative. And then once we have that linear equation, we will proceed to solve the linear equation using the method that involves the integrating factor. So let's consider this equation. We have an equation that also contains information on the initial conditions. We will exploit that to have an exact value of some constant of integration. But first, let's rearrange this a little bit. So if we move a term here, so we have the derivative of y on the left-hand side, and let's move 2y to the left-hand side of the equal sign. And so the right side stays as e to the 3x times y squared. Okay, and with this form, we express the equation in that particular format that we call Bernoulli. So in particular, p of x here is going to be a constant function of x minus 2, and that coefficient multiplying the power of y, here q of x, is going to be an exponential function. In fact, the power in this case would be n equals 2. It's a second power. So we're going to define v, the new variable, and this is where we're doing the substitution, as a power of y. Okay, so v would be defined as y to the 1 minus n, which in this case is 1 minus 2 or minus 1. So v would be y to the minus 1. So let's remember that we're assuming that y is a function of x. And by defining the new variable v in this way, we're saying that v is a function of y, but let's remember that what we just wrote there, y is indeed a function of x. So in this way, we're really assuming that v is also a function of x. Okay, so we can differentiate v with respect to x. We have to make use of the implicit differentiation here, and this calculation would give us minus 1 y to the minus 2 times the derivative of y with respect to x. So in this expression, we can solve for the derivative of y with respect to x. We have to multiply or divide accordingly by something, and so we would end up with dy dx equal to negative y squared times the derivative of v with respect to x. So let me give a name to this equation, okay? And let's say that this equation is going to be called equation 1 in our calculations here. This expression that we found for dy dx in terms of the new variable for the substitution, we're going to call this expression number 2 here in square brackets. So what comes next is that we're going to substitute expression 2 into expression 1, okay? So we're going to replace that derivative of y with respect to an expression 1 we're going to substitute and replace that with this expression we have in 2. Okay, and so we obtain this new expression. Now the left-hand side of this ordinary differential equation has dv dx, and let's make sure that this derivative of the new variable v stands alone with a coefficient of 1. So let's get rid of this negative y square. So let's divide on both sides of the ODE, divide by negative y square. And by doing so, we now obtain the derivative of v plus this expression equal to the exponential of 3x. Now, this term here, y to the minus 1, we're going to invoke that our substitution, okay, our substitution in this step, we have that y to the minus 1 is precisely that new variable v. So we can rewrite this expression, substitute y to the minus 1 with the new variable v, and so this expression here is now, we can call this number 3, and we can say that so expression 3 is linear in v and its first derivative here, let's say v prime. So expression 3 here is linear in terms of the function v and its first derivative, and so what we want to do now next is to apply this method of integrating factor to find a solution to this linear equation. So we define a function r of x as the exponential of an exponential with an argument that is equal to the integral of the function that is multiplying v here. And so that function is actually a constant function in this case too. And so from this calculation, without loss of generality, we assume that the constant of integration for that argument of exponential is 0. And so we end up with e with argument 2x. So what we do next is that we multiply every term in equation 3. We multiply every term by r of x. In other words, multiply e to the 2x by each in both sides of equation 3, and we obtained this expression we have right here. And so this would imply that on the left-hand side of this differential equation, we have the product, the derivative of the product where this is a factor, the factor e to the 2x multiplying the function v. So that's what this left-hand side is kind of writing the product rule in reverse. And on this is what the left-hand side of the ODE is. And then the right-hand side of the ODE is negative e to the 5x. Okay, so what we do next is that we integrate in both sides of this equation. We integrate in both sides of this equation with respect to x, which implies that the left-hand side is e to the 2x times v. A constant of integration, I'm calling it c1, appears on the right-hand side, and we have to deal with this integral. So here we have c and 1/5 e to the 5x is what we get on the right hand side, and the left hand side, let's still write this term. So what we have to do next is to solve for v. And to do so, to solve for v, we can multiply by e to the minus 2x, or we can divide by e to the 2x. We can divide by that term in both sides of the equation, or multiply by e to the minus 2x in both sides of the equation. So that gives us v equals to this expression. This is almost finished here. The only thing that we have to do is we need to take care of that constant of integration c1. And also, this time for the, we had made a substitution to make it this far, and it's time to unsubstitute. So v is, by definition, we constructed v by defining v as y to the minus 1, and that was obtained by defining v as y raised to the power 1 minus n, which in this case n was 2. So that's what v is, and so we obtain here that v also is, following from the previous line, is e to the minus 2x times this expression. So we have obtained a relationship, an expression that involves y, and it also involves x on the other side. In fact, this is 1 over y of x. So what we need to do next is to evaluate. Remember, we have information on the initial condition, right? So the initial condition tells us that at 0, y takes the value of -1. So 1 over y0 would be 1 over -1, because that's what y of 0 is. And then on the right side of the previous expression, we evaluate x at 0. So this is going to lead to an expression for which is easy to solve. What we want to do next is we want to solve for c1. And a few steps here of algebra would lead us in the way of finding that c1 is -4/5. So now we're ready to provide an expression for y. And with that value of c1, therefore, that's what this little triangle, this triangle of points, therefore, we write 1 over y equals e to the minus 2x times quantity. We no longer write c1, we can simply write the value of that constant, which is -4 divided by 5, minus e to the 5x divided by 5. And this is exactly the solution that we obtain for the Bernoulli differential equation. That is the equation that we have. That's the equation that we have here defined as equation 1. The solution of this equation 1 with that value of initial condition is given by this expression here.